Hello, physical science students. This is our last concept for Unit 1, Work and Simple Machines. We're breaking it up into two parts. Today we're just going to talk about work and simple machines, and then our next day we will talk about mechanical advantage. So our goal for the day is to be able to understand what is work, how to calculate work, also be able to identify simple machines and how the machines make work easier. All of this concept still deals with standard SPS 8D. I can talk, really, I can. So, work. From a scientific perspective, what do scientists mean when they say work? Well, work is simply defined as a force exerted for a distance. So, in order to do work, you have to have a force that moves over some type of distance. So if you're pushing on the wall all day long, your muscles are going to get tired, but if that wall doesn't move, you're not doing work. So no movement yields no work. Now it is interesting to note that work has a unique unit. The unit for work is joules. And a joule is defined as 1 Newton meter. So remember, force was measured in newtons, distance is measured in meters. So work is the product of the force over the distance that the objects move. Now, work also depends on the direction. So the direction of my force and the direction that the object moves has to be the same. So like, for example, got to get it in the screen. And I'll use a little object so it'll fill all on the screen. Okay. So I have an object here. If I am picking it up, my force is going up. The object is moving up, so I'm doing work. But if I push it up under the bottom, no, I'm still pushing. It's still going up. Brain fart, brain fart. If I'm pulling down and it's going up, I'm not doing work. We'll see this with pulley systems. So I'm moving one direction. The object's moving in a different direction. We're not doing work. Work, the direction of the motion and the direction of the force have to be the same. So example, lifting some books. So the books are moving up, my force is going up. Yes, we're doing work. Flipping flapjacks. Sorry, dog scared the snot out of me. So because they're in the same direction, work is being done. Oh, yeah, that was the analogy I wanted to use. Carrying the books. So if I'm carrying anything, my arms might get tired carrying books from one side of the school to the other, but because I am holding the books up, my force is going up, but my motion is going forwards. By definition, we're not doing any work because those two arrows are not going in the same direction. So pushing, not pushing, bad misreads. Carrying anything is not work. Pushing could be work. If I'm pushing forward, it's going forward, I'm doing work. If I'm pushing and it's not moving, not doing work. So those two happen to be perpendicular, but basically if they're not going the same way, no work. So you guys try and read these 6 scenarios and see if you think work is being done or no work is being done. So, scientist delivers a speech to his peers. Well, he's standing still. He's not moving. So there's no work because there's no motion. So, a man carrying groceries to his car. So, humor my lovely little bag, but we are holding the bag up against gravity, but we are moving forward to the car. They're not going in the same direction. We're not doing work. All right, a dad pushing a baby in a buggy. Don't judge my little baby buggy, but so the dad's pushing forward, the stroller is going forward, therefore, yes, work is done. A bodybuilder lifts 350 pounds above his head. So key here is lifts. So he is pulling up on the barbell, because you know it starts down here. He's pulling up and the barbell is moving up. So yes, work is done. A mom carries her baby from room to room. So carrying means I'm holding the object up against gravity. So I'm pushing up underneath. I don't care how you're holding that baby. You're supporting it from the bottom. Don't judge my baby. That's a sad looking baby. Oh well, baby feet. But the person is moving forwards or backwards. They're not in the same direction, therefore we are not doing work. Tug of war. Well, both parties on the tug of war are pulling, but the rope doesn't move. So there's no motion, which means no work. Now, calculating work. Remember, this formula is on your formula sheet. I encourage you guys to add to your formula sheets the units of measurement so that you can have a visible reminder of what everything is measured in. Work is measured in joules. So your dad goes to work to buy your mom some joules. Force is measured in newtons. So Newton's got the force. And distance is measured in meters. I don't got a cute way to remember that one. Sorry. Just distance is meters. So these are the conversions to get from 1 Newton meter to 1 joule. But just think of it as trading out. You know, instead of having $1, I'm going to trade you for 4 quarters. They're equivalent units. We can easily trade them in and out. Now remember, those of you who don't like the math, we can plug any of our 3 variable equations into our lovely magic triangle. So draw a triangle with an uppercase T. Look at the equation and see what the equation is doing. So F is beside D. That means they're being multiplied. So I have to fill in F and D on the bottom of the triangle, which means work has to go on top. This fixes it so that I don't have to ever do any algebra. So let's say that I wanted to solve for distance. Well, I cover the D up, and it tells me that work divided by force will give me distance. Ignore the little green scribbles for the moment, but can do the same thing with force. I cover it up, and it tells me that work divided by distance gives me force. So that magic triangle saves you from having to do the algebra. If you want to do the algebra, you can. Right now they're being multiplied. The opposite of multiplication is division. That is how we are getting from one equation to the other. So let's look at a couple of examples. Remember our 3-part approach. Write your givens, write your equation, solve. This makes your life a lot easier if you have everything nice, pretty, black and white on your paper, or whatever colors you like to use. So I did not mean for it to do that, but whatever. So the first thing that I see is I see joules. I have to know that joules measures work. Whether the problem tells me explicitly or not, I need to know that joules measures work. Next, I see 75 meters. I should know that meters measures distance. So we're trying to find our force, which means I cover that part of the circle. My equation is force equals work over distance, which means we are dividing. If you would like, you are welcome to plug the numbers into the triangle. I do not care how you show the calculation. I just need to see the calculation in addition to the answer. So work has to go on top, 375 joules or 375 Newton meters. 75 meters goes on bottom. And if I looked at my units, meters cancels. So I take 375 and divide it by 75. Remember that Desmos calculator, you got that fraction button that you can use, which makes life a lot easier. All right, so let's look at another work problem. Looking at another work problem. So find your givens. Newtons. Newtons measures force. Newton's got the force. So I've got a force of 30 newtons. And I've got a distance of 1.5 meters. Meters measures distance. Write down your givens with their variables so that you know exactly which number goes where. So this problem is asking for us to find work. So I can just use the equation as it's written on the formula sheet. I don't necessarily have to use the triangle. I can, but I don't have to. So force times distance gives me my work. Remember this three-part approach, your given, your equation, and your solve, can make word problems a lot easier. At a minimum, you must show the solve portion. Having answers only will not get you full credit on any of the practice. I highly encourage using this three-part approach, though, because it makes the math of physical science much easier. So, even if I was doing, what was the first? A distance one, the process is still the same. Use the units and the problems to set up the problem, and then just plug and chug into your calculator. So the second part of today's lesson is dealing with simple machines. What are our different types of simple machines? This should seem a little bit familiar because you probably saw a lot of this in physical science. So what's a machine? Well, a machine is anything that makes work easier. And there's three different ways that a machine can make work easier. A machine can make work easier by either increasing the force, so basically it kind of makes you stronger. Think a car jack. You're not able, most people, to lift a car by itself, but that car jack, by turning it over and over and over again, makes you stronger so you can lift the car. It increases your distance. That's the second way it can do it. So think of it as ramps or like a spiral staircase or a winding road. You're traveling a longer distance so that you can not have to climb as steep of an incline. And last but not least, the third way that machines make work easier is by changing the direction of the force. So blinds, curtains, flags, flagpoles, those type of things, those all change the directions of your force, which makes the job easier. So 3 ways that machines make work easier. They increase your force, they increase your distance, or they change your direction. Oh, isn't that cute? So, when we're thinking about machines, you have to put in work. Input is what you do as the person using the machine. Output is anything that the machine puts out. It can be an output force or an output distance, but output is what you get out of the machine. So there are 6 basic simple machines that we look at for physical science. These machines can come together to form more complex things, and some of them we're going to kind of briefly discuss how they combine. So first and foremost is an inclined plane. An inclined plane is simply a sloping surface. So you can think of it as a ramp, but things like a mountain road or a spiral staircase, those are all also inclined planes. What they do is they increase your distance. So if I was trying to take this green box, I'd have a choice. I could just lift it straight up. Let's say that's 5 meters. Or I could slide it up this ramp, which looks to be about, I don't know, 3 times longer. So we'll just say 15 meters. Or I can slide it up the ramp. Well, it's much easier to slide it up the ramp than it is to try and strong arm it up the 5 meters. So our second type of machine is a wedge. And a wedge are two inclined planes brought together. Wedges typically have points. So think of axes or knives or blades. Those are typically wedges. And what they do is they push in between objects and force them apart. So hatchets do this. You can actually quite literally see wood breaking apart. But so do knives and blades. You may not realize it, but as you're using a knife to cut a piece of bread, you're separating the bread into pieces. So a wedge is just two inclined planes put together. There are a few wedges that only have one side that comes kind of to a point, but for the most part, most of the ones that we play with or encounter have two. So a screw. A screw is an inclined plane wrapped around a cylinder. So the obvious thing that's a screw is, of course, the utensil, the thing that's a screw. You screw things together when you're putting them together. But there are other things that are actually screws as well. So a spiral staircase, depending on how you look at it, could be considered a screw. It's an inclined plane and it's wrapped around a cylinder. If you've ever twisted something around your paper and you ended up with that edge that's on that outer part, you've made a screw. So the screw travels that green distance, or is moving, that's the machine's distance. But me, as the user, I have to turn it, and that turning takes the entire blue path all the way around. So it increases the distance to make me stronger. So a lever is another type of machine. And it is simply anything that can rotate around a fulcrum. So anything that can pivot around a fixed point. That fixed point is called a fulcrum. So I was looking for scissors. I almost always have scissors handy, but I don't have scissors handy at the moment. So I've got fulcrums here. The legs of my normal microphone, they are pivoting around a set point. That set point being right here at the base. Scissors, picture the same thing. You pull on the handles and they pivot around that center screw. Those are all examples of levers. A wheelbarrow, the fulcrum is closer to the front versus like a seesaw or some of the lifts that you might see in construction where the fulcrum is more in the center. Now levers can do different things. They can increase your distance or they can change your direction. So this particular example here changes direction. And it also increases distance. Notice that there's a longer piece on the left than there is on the right. Change direction, increase distance. So where my wheelbarrow, it doesn't really change the direction, it just increases the distance. I'm pulling up further away, which makes it easier to lift the load. bottle cap removers, brooms, rakes, your arms and your legs, your appendages, those are all different types of levers. They can rotate around a fixed point. So my elbow is the fulcrum, and it's rotating around that point. So wheel and axle. A wheel and axle is considered a simple machine, but it's, kind of two things together. You've got a wheel that spins, and it has to be connected to, there we go, it has to be connected to an axle, which is basically just a wheel of a slightly different size. So screwdrivers are great examples of something you wouldn't think of as a wheel and axle. So I've got my larger wheel, I've got my axle, and I've got my smaller end. So what is this supposed to be? I think it's supposed to be a well bucket. So the larger surface, that smaller area connected by some type of a fixed pole. That fixed pole is your axle. The things that they spin around are your wheels. You've got the obvious things like wheels on a car, or steering wheels in a car, or handlebars on a bike, or wheels on a bike. But there are other things that involve spinnings around an axle. Usually wheels and axles almost always increase the distance. So it makes you stronger. It increases your work by increasing the distance that you move. I'm 99% positive this is the sixth simple machine. Our last simple machine is a pulley. And a pulley is simply some type of cord. It can be a cord or a chain that is wrapped around a wheel. So as we move the cord or we move the chain, the wheel rotates. Pulleys can have very, very simple arrangements. So like the one that I just put the blue box around, it's probably similar to what you would see with your window blinds. You pull down on the handle, so the green part, and the blinds move up. So the load moves up. But you can get more complex pulley scenarios. The more times the rope wraps around different pulleys, the stronger the pulley is. The more the pulley will make your job easier. Now, most pulleys that you will see in the real world, you end up using by pulling down. So you can see this person, they're pulling down. The green one I did earlier, they would have to pull down. All of the ones in this lovely little image, they all pull down. But there are a few pulleys in existence that, yes, you do have to pull up. So that one, I'm pulling up, and my load, which is this, moves up. So it increases the distance, but it doesn't change the direction. Most other pulleys are changing the direction. I'm pulling down, the object's moving up. So that is it for today for our simple machines and work. Make certain that you attempt your practice that corresponds to this in Google Classroom. If you're having any challenges with any current content or any previous content from Unit 1, please come into my open office hours or schedule an individual tutoring session using our calendar schedule on my Google site. That is it for work part 1. Dad, net it.